All right, guys, I'm just going to continue working through problems of 11.7 for the purpose of reviewing for test 3. Okay, so we're at number 11. I'm going to go kind of fast. Hopefully you guys know some of the material well enough to understand what's going on. Okay, so we have this series. So how would I write up the solution for this one? I would say, let's see. Remember, just in general, when we have series AN that's convergent and series BN that's convergent, then AN plus BN will be convergent and equal the sum of the series. Okay. So how would I write out this problem? I would say note 1 over n cubed convergent by p-test. And 1 over 3 to the n convergent by geometric series test. So 1 over n cubed plus 1 over 3 to the n equals is convergent. And we can say there's a theorem for this in section 11.2. We can say by properties of convergent series. Okay. It's important to note that we can only split this series up into 2 separate series if both of these are convergent. Okay. So for example, okay, so that's the end of this problem. Just a counterexample real quick. We have 1 over n minus 1 over n plus 1. Okay. This is a convergent telescoping series, but we can't split it up into 2 separate series. Okay. Because now these are both harmonic series, these are both divergent. So it wouldn't make sense to split it up. I'd have infinity minus infinity, right? So that doesn't work. 12. Okay. So looking at this is close to a polynomial, right? On the bottom, if I didn't have this plus 1 here, I'd have square root of k squared, which would just be k times k. So I basically have 1 over k squared, okay? So if I'm trying to compare this to something, I would want to compare it to 1 over k squared, right? Let's see, and we should actually, this should be k. All right, so how does the comparison go? Let's see. Well, first of all, this is convergent by p-test. Okay. So let's see. To do comparison tests, what do I need to do? I need to check everything's positive. Okay, so if that's my AN and this is my BN, okay, well, AN, BN greater than or equal to 0 for all n. Okay, there's not much to check there, it's true. And then what do I need for comparison test? I also need the inequality going the right way. So if I want to show this is convergent, remember I need less than this to be less than or equal to this. Okay, so let's see. K squared, let's see, is less than or equal to k squared plus 1. So, yep. So square root of k squared is less than or equal to square root of k squared plus 1. So then when I turn that into a fraction, the inequality flips. Okay, and if I multiply by k, nothing changes, right? Okay. All right. And then the inequality flips here. Okay, so what do I have? This is my stuff on the left side. It's less than or equal to the stuff on the right side, right? All right, so I'm good. So I got AN is less than or equal to BN for all n. So how do I conclude? I would say 1 over k squared convergent by p test. So 1 over k squared plus 1 convergent by comparison test. Okay, so I got 13, 3 to the power n squared over n factorial. N factorial makes me think I should at least try a ratio test, so let's try that. So I need an plus 1 over an. Okay, let's see. An plus 1 would be 3n plus 1, n plus 1 squared, n plus 1 factorial. Dividing by an means multiplying by the reciprocal. Okay, simplifying. So we get this. Simplifying factorials. Let's see, what do we get? We could combine these squares. We end up with this, right? Now the question is, what's the limit of this thing? As n goes to infinity. Okay. Think about it piece by piece. This 3 is just constant. I can bring that outside. What's the limit of n plus 1 over n squared? And then I could kind of break it up into pieces like this, right? So I got this limit times this limit. Okay. This limit's 1. Limit of n plus 1 over n is 1. And then if I'm squaring it, it's still 1. And then the limit of this is 0. So I have 3 times 1 times 0 equals 0. So to conclude, I would say, what does the ratio test tell me? It tells me if this limit's less than 1, the series is absolutely convergent. So I would say my series is absolutely convergent by a ratio test. So convergent, because absolutely convergent implies convergent. All right, number 14. This is another good one to show the power of absolute convergence. Okay. If I was looking at this, okay, trig stuff, I'm going to use comparison test a lot. But if I was going to try and compare this to something, remember, what do I need to check for comparison test? Everything's greater than 0 is one of my conditions, right? I need my series AN and my series BN, whatever I'm comparing it to, whatever my BN is. I need all those to be greater than 0. But sine of 2n can be negative, right? Depending on what n is. Okay. So instead of considering this series, I would, how I would do this, I would say, and I would actually write this. I would say consider sine, absolute value of sine of 2n, the absolute value. Okay. Now, okay, if this is my an, okay, what can I compare this to? Well, sine of 2n, absolute value, it's greater than or equal to 0, and it's less than or equal to 1. And I would say, and also consider this series. Let's see. And in fact, we can simplify it to 1 over 2 to the n. Okay, let's say this is our b to the n. I would say, okay, now do I have everything's greater than or equal to 0? Yeah, right, because absolute value, that's always greater than 0, and then 1 over 2n, that's always greater than or equal to 0. So my stuff's always greater than or equal to 0. Check. Now, can I compare these two? Is the comparison test going to work on this? Well, let's see. This is convergent, right? And so I want to show this is less than or equal to this. And I could do this in steps. I could say this is less than or equal to 1 over 1 plus 2 to the n, right? And then I could say that this is less than or equal to 1 over 2 to the n, because I'm dividing by a larger number here. So just to sum up, I could say, boom. Okay, so I got my second condition. I got my inequality. Then I would say 1 over 2 to the n is a convergent geometric series. So there's going to be a lot here. Sine of 2n over 1 plus 2n, absolute value. Convergent by comparison. So sine of 2n, since this is the absolute values of my original series, I would say this is absolutely convergent. So it's convergent. So a lot there. Okay. But if you wanted to list every step and be like 100% thorough, that's how I would do it. This one looks a little weird. Okay, so I got 2 to the k minus 1, 3 to the k minus 1, and then k to the k. So if these were k's, I would think root test, right? Everything would be to the power k. So can I still do root test on this? Yeah. And there's a couple ways I could do it. The way I would do it is I would say, you know, the series we're starting with, okay, I would say I can make these into k's if I divide by 2 and divide by 3. So I'd say this series is the same as 1 over 2 times 3. Okay, then I can write it as 2 to the k, 3 to the k over k to the k. Same thing, right? Okay, all right. So I would say, okay, let absolute value. Now let's try root test on this. So, okay, so I'll say an equals 1 over, we can simplify this to 1 over 6, 2 to the k, 3 to the k, k to the k. Then I would say, okay, well, let's see, since we're dealing with k's, that should be k. So kth root of absolute value of a to the k, what's that? Okay, now I just take the kth root of everything. Okay, so that would be kth root of 1 over 6 times kth root of this. Okay, so now I take the kth root, the kth root and the power of k cancel and everything. So I would get 6, 2 times 3 over k. All right. So this is what my kth root of ak is. Okay. Now, what's the limit of kth root ak? Okay. If I have any constant and I take the limit of the kth root of the constant, it's going to go to 1. Okay. Think of like square root of 10, cube root of 10, fourth root of 10. The bigger that root gets, the closer it's going to go to 1. It's not going to go to 0. It's going to go to 1. Same thing with fractions. All right. This is going to go, the limit of this is going to go to 1. And then what's the limit of this as k gets big? It's 6 over k as k goes to infinity. That's going to be 0. Okay, so the limit of this thing is going to be 0. All right, so how do I conclude? I would say limit of kth root absolute value ak equals 0. So my series, I can write out the series again. My original series is convergent. Well, I could say absolutely convergent. Absolutely convergent by root test. Okay, so 16. What I have here is almost polynomial over polynomial, right? I'm taking square root. should still be basically, I can basically think of this as polynomial over polynomial, which makes me think maybe comparison test, right? So first, let's figure out what I should compare it to. And let's first kind of mentally erase everything that's not too important. So if I got rid of the 1, I'd have square root of n fourth, which would just be n squared, right? If I got rid of the n, I'd just have n cubed. So maybe what I should compare it to is n squared over n cubed, which is equal to 1 over n, the divergent series, the harmonic series, right? So maybe, that's kind of giving me the hint that maybe this is divergent as well. So how can I show that? Comparison test, maybe, but I maybe from experience know, since, okay, if I try and compare this thing to, let's say, n squared over n cubed, let's see, this denominator is bigger, but it's kind of counteracted by the fact that this numerator is bigger, but it's counteracted by the fact that this denominator is bigger. So I'm not going to be able to get a good inequality saying that this is greater than or equal to my divergent series. So I can tell from experience that what I should actually do is limit comparison test. Okay, so that's what we use when we can't get the inequality going the right way on the comparison test. Okay, so I'll say, all right, I'll say an is my n to the fourth plus 1 over n cubed plus n. And I'll say my bn is, I could use either one of these. Let's go ahead and use 1 over n. Okay, oh, 1 over n. Then an over bn equals, okay, let's see, n to the fourth plus 1 over n cubed plus n, right? And then let's see. Okay, this is, I could say that this is, well, we don't have to say greater than or equal to. Let's see. Let's just try and simplify this a little bit. So we can cancel out this n from the top and bottom, right? We get n to the fourth plus 1 over n squared plus 1. Okay. So let's see. If I take the limit of an, okay, maybe I'll be a little bit slapdash with this. Okay, what is the limit of this? The limit of the top, limit of square root of n to the fourth plus 1, okay, over n squared plus 1. Basically what I have here is n squared, right? The bigger n gets, the less that 1 matters. So, okay, this is essentially n squared, and then the bottom is essentially n squared as well, right? The plus 1 on the bottom matters very little as n gets big. So the limit of this, I basically have n squared over n squared, which is 1. If I wanted to show this more rigorously, maybe I could turn these into functions of x and use L'Hopital's rule and then argue that the function of x and this sequence would have the same limit. You could do that if you want. All right. So limit equals 1. So what does limit comparison test tell me? It tells me, okay, I would say limit an over bn equals 1, and the series 1 over n diverges. So sequence n to the fourth plus 1 over n cubed plus n diverges by limit comparison test. All right, onward. 17 is weird. It looks kind of similar to factorial, right? I got 1 times 3 times, I got a bunch of stuff. I could think of this as like 2n minus 1, and then I'm multiplying by a lot of integers below that going down to 1. So kind of like factorial. And then similar on 3, the denominator, 3n minus 1 times blah, 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 working my way downward down to 2. So these aren't factorials, but maybe they behave similar to factorials. So think about, what test should I use when I have factorials? ratio test, right? You know, that should be the first one I try. So let's try it and see what happens. Okay, so I need to figure out what an plus 1 over an is. All right, so let's see. An plus 1, let's write out an plus 1. That'd be 1 times 3 times 5, up. And then what would I have? 2n minus 1, and then the last term would be 2. I'd replace n with n plus 1, and then, you know, distribute the 2 and subtract the 1, and I should get 2n plus 1, right? And then, okay, what would the denominator be? It'd be 2 times 5 times 8, blah, blah, blah. 3n minus 1, and then I'd plug in the n plus 1, and let's see, after simplifying, I get 3n plus 2, right? So this is just an plus 1, okay? And then I want to divide by an, okay, which means I want to divide by, let's see, an, which would be 1 times 3 times 5 to 2n minus 1 over 2 times 5 times 8, 3n minus 1. Okay, so what cancels? Remember, I could multiply by the reciprocal, right? All right, so what cancels? You can confirm this for yourselves, but let's see, what's going to cancel? I'm going to end up with all of these 1, 3, 5 to 2n minus 1 is going to cancel, and I'm going to be left with 2n plus 1. Okay, what's going to cancel from the denominator? The 2, 5, 8, 3n minus 1. I'm going to be left with 3n plus 2. Okay, so I got an plus 1 over an equals this, 2n plus 1 over 3n plus 2. And then what's the limit of an plus 1 over an? Well, 2 over 3, right? I would say, all right, so what does ratio test tell me? It tells me that this thing's absolutely convergent, so it's convergent. So I would say we can call our series an is absolutely convergent by ratio test, so convergent. 18's really straightforward. It's just alternating series. If all we need to show is that it's alternating series test, or excuse me, if all we need to show is that it's convergent or divergent, it's simple. It's just alternating series test, right? Something more interesting to do would be what if the instructions are determine if it's absolutely convergent, conditionally convergent, or divergent. So let's try that. So remember, let's see, if I did ratio test, I'll kind of spoil it for you. If I did ratio test, I would get the limits equal to 1. Okay, so limits equal to 1. So it's not going to be absolute. Well, we don't know, right? That's the inconclusive case. All right, but remember what I said when we get the limits equal to 1, that inconclusive case, that's usually going to be conditionally convergent. So let's try and show it's conditionally convergent. So what's the first thing I do? I show the absolute values are divergent. So I want to show that the absolute values are divergent. So let's see. If I do the absolute values, I get 1 over square root of n minus 1, right? And let's see, that would be greater than or equal to 1 over this series, because I'm dividing by a smaller number on the left. Okay, this is a divergent p series. So this is divergent by p test. Okay, now I need to check my conditions for comparison tests. Okay, I need to show everything's greater than or equal to 0. I'll call this a. Okay, so an, bn greater than or equal to 0. Boom, good. And then I got, let's see, an greater than or equal to bn for all n. Boom, good. All right, so I would say, call this, I would say 1 over square root of n minus 1, divergent by comparison test. Okay, so the absolute values diverge. Now let's try and show the original series is convergent, and again, that's just alternating series, right? Okay, so my original series convergent by AST. And then to wrap up, I would say something like, since AN's convergent, but absolute value of AN divergent series is conditionally convergent. Okay. This is another one that if you tried the ratio test, you would get a limit equal to 1. So that tells me it's probably going to be conditionally convergent. So let's just try and show it's conditionally convergent. Let's see, what do I need for that? I need to show this is divergent. Okay. So let's see, if I consider the series of absolute values, I get ln of n over square root of n, which is greater than or equal to, let's see, if for n equals 2, okay, if I started at, let's see, actually, if I started at 3, this would be greater than or equal to 1 over n, right? So if it's greater than this eventually, that's enough. Okay, so this is divergent. So this is divergent by comparison test. Boom. I'm being sloppy here. I'm not showing all the conditions. Hopefully you guys now have watched several of these problems and know what you got to show. Okay. So this is divergent by comparison test. So my series of absolute values diverges. Boom. All right. So I did that. And then what do I need to, what else do I need to show for conditionally convergent? I need to show that my original series is convergent. That's going to be by alternating series test. By alternating series test. Why? Because square root of n is going to grow a lot faster than ln of n. So this limit's going to go to 0. It's alternating series. Terms are decreasing. Yeah. So by alternating series test, my series an convergent. So boom, conditionally convergent. All right, let's do 20 and I'll stop. I'm thinking comparison test on this one. So let's see, if I only had the most important stuff, what would that series look like? Well, k to the cube root, that'd be same thing as k to the 1/3, right? And then what about on the bottom? I got k times square root of k. That's basically k to the 3/2 if I ignore that 1 there. Okay, so what would this be? This would be 1/3 minus 3/2. That looks like it's k, 1 over k to the, what, 7 over 6? All right. So what's going on with this? This is a convergent p series, right? Convergent by p test. Because 7 over 6 is greater than 1. All right. Now, let's see. Is everything greater than or equal to 0? Yeah, so if this is my an, this is my bn, everything's greater than 0. Boom. Let's see if I can do the direct comparison test. Now I need my inequality going the right way. If I want to show this is convergent, I need to show that this is less than or equal to this. Okay. So these two are equal. Let's try and compare this to this. That'll be easier. Cube root of k minus 1 is less than or equal to k to the 1/3, which is the same thing as cube root. Okay, so this numerator is less than or equal to this numerator, all right? And then what's going on over here on the left side, I'm dividing by a larger number. Yeah, okay, so I still have less than or equal to. Okay, so my inequality's gone the right way. Boom. So I'm done. I just need to wrap up. It's my convergent test, right? So I would say 1 over k to the 7 over 6 convergent by p-test. So I'll call it an convergent by comparison test. All right, I'll stop there.